So the situation is we have a table. So we have a table. And then we have a pile of chain sitting here at rest. And we're told that this pile of chain is frictionless. So it's completely smooth. And it has a uniform density of sigma kilos per meter. So the situation is someone starts to pull the chain downwards. So after a while, part of the chain is being pulled downwards. And so you can imagine a hand here pulling the chain downwards. And it's being pulled downwards at a constant acceleration of a. So the problem is how much force is being exerted on the chain at this point. So we want to find the force as a function of time. So how do we do it? So first of all, let's find the momentum of the entire system as a function of time. So if you see here, the momentum of the entire system comes from two parts, right? First of all, it comes from the stationary part here, which of course has zero momentum, and it comes from the moving part here. So the momentum of the entire system is really just equal to the momentum of this moving part here. So using that, momentum is equal to mass times velocity. And what is the mass of the moving part? Well, let me just let the length of the moving part be x. So mass is equal to x times its density. So this is our mass. With velocity, since we're being told that it's being accelerated at a constant rate of a, the velocity is just acceleration times time. And then, since the acceleration is constant, we can actually just use our equations of motion to find x as a function of time. So we can actually use this formula. S is equal to ut plus 1/2 at squared. So the chain was initially at rest, so this is just 0. So x is equal to 1/2 at squared. And so just substituting that in, we have an expression in terms of time that gives us the momentum of the entire system, a squared t cubed. So taking the derivative with respect to time, on the right hand side we get 3/2 sigma a squared t squared. So why did we take the derivative? Because the change in momentum with respect to time is equal to the net force acting upon the entire system. So what is the net force? So notice that in these equations I've taken the downward direction as positive. So what forces do we have acting upon this entire system? So first of all, we have gravity. So the gravity acts on the stationary part, so this part. So the gravity acts on this stationary part, but it also has a normal force coming from the table that is keeping it still on the table. So those two forces cancel out, but we still have gravity acting upon the moving part of the chain, and nothing is going to cancel that out. So we're going to have to consider the gravity acting on that part. So what is the gravity acting upon the moving part of the chain? Well, obviously it's just the mass, x, sigma, times gravity, g. So don't forget x is equal to 1/2 at squared. So what other force do we have? So also we have a force from our hand that it's pulling the chain downwards. So we plus ft. And so there we have it. Once we solve this equation, we will find the function that we're looking for. So let me just open a new page. So let me just copy down where we left off. So 1/2 sigma agt squared. So that's this term here. Plus the force is equal to 3/2 sigma a squared t squared. So let me just, obviously we can move this term to the right. So ft is actually equal to 3/2 sigma a squared t squared minus 1/2 sigma agt squared. And if you notice, we can actually factorize this whole thing into something pretty nice. So let's take out the 1/2 and then take away the sigma. And we can also take an a. And then we can also take the t squared. And then we're left with 3a minus g, so we can just factorize that. And so there we have it. This is our formula. So maybe a better way to write this would be 3a minus g. So keep the constants on the left. So there we have it. This is our solution. So this formula here gives us the force of the hand. So this is the amount of force that the hand is acting upon the chain as a function of time. So if you notice, when acceleration is equal to g/3, actually the force is going to be equal to 0. So when the chain is being pulled down at some certain acceleration, if the acceleration is equal to g/3, the hand actually doesn't need to do any work at all. You can just let the chain fall and it will fall at this constant acceleration. And so there we have it. This is the solution to this problem, and I hope this helped. I'll see you in the next video. Bye.